Hello everyone, welcome. This is the last lecture of this week. We'll consider one more example on frame, but the frame undergoes sway. So, the example that we consider today is this. If you see the similar example, similar frame problem, but all the dimensions and loadings are same, but in addition we have another 10 kilonewton load, a horizontal load at B, which will cause the frame to sway in this direction. Okay, let us the dimensions and loadings are taken same, because some of the results that we have already obtained in the previous class, we can directly use them. Okay, so this is the example. Okay, now this is the frame, which is there is a horizontal load. There is a horizontal load here. Okay, now because of this load, what happens, if you remember, if there is no load here, it is just a problem like this. Okay, then the beam may the frame may deform like this. It is if it is only subjected to vertical load on BC, there is no horizontal load, then probably the beam may deform like this. This is the deformation of this, and this is the deformation of this member, and then similarly this will be the deformation of this member. Okay, this is the probable deform behavior of the structure when it is subjected to only vertical load on BC. Now, this is only vertical load on BC. Now, in addition to that, if there is a horizontal load as well, then what happens, the beam will undergo sway like this in this direction. Okay, then the beam may deform in addition to this deformation because of this horizontal load. So, this point B, this is A, B, C, D, point B moves in this direction, point C also moves in this direction. So, this become something like this. Okay. Your deformed shape becomes something like this, and this is A, B, C and D. Now, point B goes to B dash and point C goes to C dash, and this distance is delta. Okay. Now, since we assume there is no actual deformation in BC or in any member, so the amount of sway takes place at B, the same amount of sway will take place at C dash. Okay. So, B dash is equal to delta, and similarly C dash is equal to delta. Okay. Now, if you compare this problem with the previous problem, and what are the changes we need to do? You see, in the previous problem, all the steps are again overall the steps are same. Let us first start the steps, and we will discuss what are the differences. Now, the first step was the step 1. Step 1 was finding the fixed end moments. Okay. Now, again similarly, since this joint is acting this force is acting at the joint, this force will not cause any moment in this moment in this member, and in this member in the primary structure as well. Okay. For instance, in the primary structure becomes what? Primary structure for AB become this, for CD become this, and for BC it becomes this. Okay. And the loads are acting on it. There is no load on this, there is no load on this. There is a load, externally load is acting here, external corresponding load is here, but this will not induce any moment in this structure. This will not induce any moment in this structure, because this is acting at the support. Okay. So, what is the fixed end moment then? Fixed end moments, MAB fixed end is equal to MBA fixed end is equal to MCD fixed end is equal to m DC, again fixed end, they all will be 0. Okay. And then what is MBC? MBC fixed end moment is equal to MCB fixed end moment, this will be minus, is equal to W L square by 12, and W is 7.5, L is 10. So, this becomes 62.5 kilonewton meter. Okay. Some of the for some of the results I suggest you to refer to our previous class, because these we have already done in the previous class. We have already computed these values in the previous class. Okay. So, this is the fixed end moment we have. This was our first step. Now, second step is applying the slope deflection equation for different members, member AB, BC and CD, and the difference lies there. Okay. Let us see let us first apply the slope deflection equation for span AB. Okay. So, step 2 slope deflection equation, let us for span for AB. Okay. What is the slope deflection equation? MAB is equal to MAB fixed end moment. Let us write the general expression 2 EI by LAB, and then 2 theta A plus theta B minus 3 delta by LAB, that is the general expression. Okay. Now, theta A is 0, that is fine, because it is theta A is 0, we have theta B is non-zero, then delta is this amount. This is if we consider this is the beam, this is AB is a separate beam. Okay. Separate member, then joint rotation will induce, rotation at B will induce some moment at A and B, and then in addition to that, the settlement of joint, in this case settlement is the translation of the sway takes place at joint B. This delta will cause some moment at B dash, some moment at B and some moment at A, and so this delta is not 0. That is the difference with the previous case, where there was no sway, there was no force, horizontal force like this. So, there was your deflected shape was this. So, there was no sway at the delta was 0, but in this case delta is not 0. So, and this is also 0, this part is 0, fixed end moment is 0. Now, then this becomes MAB becomes 0.4 EI theta B minus 0.24 EI delta. So, this is the first slope deflection equation for member AB at A. So, similarly we can write the slope deflection equation for BA. MBA will be fixed end moment, MBA fixed end moment plus 2 EI by LAB, then theta A plus 2 theta B minus 3 delta by LAB. Okay. And again, if we substitute all these values, we get MAB is equal to MBA is equal to 0.8 EI theta B minus 0.24 EI delta. Okay. Now, in the previous example delta was 0, only we had these two values. Okay. So, this was for AB. Now, let us do it for BC. Now, for BC there is no, for BC there is no sway, there is no see joint B still remains in this line, joint C still remains in this line. So, there is no sway takes place for joint BC. When we consider joint AB, the settlement is the the joint settlement will be in this direction or in this direction. For CD also either in this direction or in this direction. But when we consider member BC, joint settlement means either joint B goes to here, or joint C moves in vertical direction, but that is not happening here. So, for member BC, the delta for member BC, there is no settlement. So, contribution from the settlement will be 0. So, for member BC, then a slope deflection equation will be M BCF plus 2 EI L BC into 2 theta B plus theta C. Delta is equal to, there is no delta in this case. So, this is the equation, and if we substitute this value, all the value corresponding value, MBC become minus 62.5 plus 0.2 EI 2 theta B plus theta C. This is for BC. This is for BC, and similarly we can write for CB is equal to, similar expression we get 62.5 plus 0.2 EI into theta B plus 2 theta C. So, this is for BC, this is for CB. Okay. So, again let us do it for for CD. Now, CD again there is joint settlement, the joint C moves in this direction, and that is, this direction is delta. So, contribution from the settlement of D, or in this case sway at joint C, that needs to be considered. Okay. So, the corresponding equation will become, so for CD it becomes MCD is equal to MCD fixed end moment plus 2 EI by LCD. You see, please note in these examples EI are taken as constant for all this member, but if EI is not constant, then you have to take EI for the corresponding member here. The way we are taking different length for different members, similarly the different EI for different member needs to be taken. Okay. So, this becomes 2 theta C plus theta D minus 3 delta by LCD. Again theta D is equal to 0 because it is fixed end. So, this becomes 0, and then final expression becomes MCD is equal to, and this is also 0, this is also 0. So, MCD is equal to 0.8 EI theta C minus 0.24 EI delta. Okay. So, this is for MCD, and similarly we can write for MDC, and that will be 0.4 EI theta C minus 0.24 EI delta. Okay. So, this is for DC. Okay. Now, we have already applied the slope deflection equation for each segment, and the next step is applying the equilibrium condition. And equilibrium condition is that joint at B is the MBA plus MBC is equal to 0, and MC plus MD is equal to 0. So, let us apply second step, let us apply the equilibrium condition. Step 3 is MBA plus MBC is equal to 0. Okay. This is one equation, and then equilibrium condition at C is MCB plus MCD is equal to 0. So, this is at B, and this is at C. The equilibrium conditions are 0. Now, here is an interesting point. How many unknown we have here? Rotation at B, rotation at C, and this sway delta. We have 3 unknowns, and how many equations we have? We have just 2 equilibrium equations, isn't it? The equilibrium at B and equilibrium at C. It means we need one more equation, okay. And let us see, that is the main difference that you have in problems between the problems which does not have any sway and the problems which have sway. I mean frames without sway and frame with sway. Frame without sway, these equilibrium conditions was enough to give you the sufficient information and to solve the unknowns, but in this case we need one more equation. And what is that equation? Before we come to that, let us write what is this expression. Let us substitute the expression for MB and MBC and get the corresponding expression. Now this will give, the expression becomes at B is like this: 1.2 theta b, and then plus 0.2 theta c minus 0.24 delta is equal to 62.5 by EI. So, this is the first equation, this is equation number 1, and then the second equation become 0.2 theta b plus 1.2 theta c minus 0.24 delta is equal to minus 62.5 by EI. So, this is second equation, this is equation number 2. Please once again you please check. So, this 0.2 is what? 0.2 is the contribution of theta c at B, and this part is contribution of theta c at B, and this part is contribution of theta b at C, and associated stiffness coefficients are in this case stiffness coefficient is 0.2, in this case 0.2 into EI, in this case stiffness coefficient is 0.2 EI. Again the symmetry can be observed. Okay. So, this is the equilibrium two equations that we obtained from equilibrium equation. Now, we need one more equation. The another equation that we get, that let us see what is that equation. Now, let us draw all the members separately. Okay. Now, this is the member, and this is another member, and this is another member. Okay. And this is member A. Now, this is A, B, C and D. Okay. Now, what are the forces we have? This force, this is the corresponding moment. This is MCB, M at C in member CB. This is MBC. Okay. And then we have this MBA. MBA means moment at B in member A, and then all are shown in clockwise direction. This is MAB, and then again this is MCD, and this is MDC. Okay. Now, you see, then what we have is, in addition to that we have shear forces as well. Okay. Now, what if we take moment about, in addition to that, say these are the supports, say we have a force at VA, this is the shear force at VA, and similarly we have a shear force at VD. Okay. We have a shear force at this point as well, corresponding point, say this is as well and this is as well. Okay. And we have a shear force and this member as well, but since we are only concentrating on the moment, we are not drawing it here. Okay. Now, the reason why the shear force is shown here. Now, if you would take the free body diagram of this part and take moment about this. Okay. And then what we have? We have that VA is equal to this length is LAB and this length is LCD. Okay. Now, if we take moment about A, moment about this point about B, then what is VA? Then VA will be this moment plus this moment and then divided by LAB. Okay. So, MBA BA clockwise, if then MAB plus MBA divided by LAB. Okay. This is VA. Okay. And similarly, if we take moment about this point and then what are the forces that will contribute? This will contribute, this will contribute and VD will contribute. This will not contribute because this is passing through this point. So, similarly, VD will be MCD plus MDC divided by LCD. Okay. So, this is now what is VA essentially? VA is the horizontal, this is we have a support at this point, right? We have a support at this point, So, VA essentially, which is shear force at A, it is essentially the horizontal reaction at A, as similarly VD is shear force at D, which is essentially the horizontal reaction at D. Now, if we look at the equilibrium of the entire structure, means if we look at the equilibrium of the entire structure, suppose this was the structure, this is the structure. Now, and draw the free body diagram of this of the entire structure. Then what are the free body diagrams we have? This will be a force like this, and then a reaction here, and similarly a moment and a reaction here, and then a reaction here, and then reaction here, right. Now, so this is essentially we have obtained, this is VA, this is VD. Right. Now, so equilibrium says that total VA plus VD plus this horizontal force, that should be equal to 0, that is summation of Fx is equal to 0, that is the equilibrium condition, right. So, if it is, then can we say that then summation of Fx is equal to 0 gives us, summation of Fx is equal to 0 gives us that VA plus VD plus externally applied load 10 kilonewton, that should be equal to 0, isn't it? Now, now VA is equal to this and VD is equal to this. We have already obtained the expression for MA and expression for MBA, MAB and MAN. We have already obtained the expression for MAB and then corresponding expression for MBA, and then we have already expression for MCD, and we have expression for MCD and corresponding expression for MDC. What now we need to do is we need to substitute this expression in this equation. If we do that, we get one more equation, that is equation number 3. Okay. And this, if we do that, the equation finally what we get is this 1.2 theta b plus 1.2 theta c minus 0.96 delta, that is equal to minus 50 by EI. That is the additional equation we get by considering the shear force. Okay. This is the additional equation, you can check this equation. This is the additional equation we get. Okay. And how we obtain this equation? We obtain this equation by the shear. Okay. Now, again as I said, there would be some other forces in this. This is not the complete free body diagram of each member separately, because you have some other forces here. All the forces I did not show here, because if I show all the forces, then this diagram becomes very will not be clear. Okay. So, all the forces which is contributing to this third equation is shown here. Okay. Now, so this will be equal to minus VD VA, this will be equal to Okay, okay, forget it. Now, this is, so we have three equations. Now, two equations are one equation, two equation which is equilibrium at B and C, and another equation by which is obtained from obtained for equating the total shear force with the externally applied load. Okay. Now, next step is again straightforward. Next step is we need to solve these equations. Okay. And if we do that, then this the solution becomes theta b is equal to 78.125 by EI, and then theta c is equal to minus 46.875 EI, and delta is equal to 91.146 by EI. 78.125, 46.875, this is negative, and delta is equal to minus 90.145. This is the final solution. Now, one interesting thing is, in the previous example where there was no side sway, theta b and theta c were same, but in this case theta b and theta c is they are not same. Okay. Now, once we know theta b, theta c, next step is just to apply theta b, the value of theta b and theta c in these expressions, the value of theta b, theta c and delta in these expressions, in all these expressions, in this expression to get the moments at the joints. And if you apply the moments at the joints, the final values that you get is this: MAB is equal to 9.375 kilonewton meter, MBA is equal to 40.625 kilonewton meter, MBC is equal to minus 40.625 kilonewton meter, MCB is equal to 59.375 kilonewton meter, and then MCD is equal to minus 59.375. Always write the unit, because I have seen many places that this is the common mistake we do. 40.625, you write just like this, MDC is equal to 40.625. This doesn't carry any meaning. Okay. When you write it is kilonewton meter, then it carries some meaning. Okay. So, anything you write, always write the corresponding unit with it. Without unit, any data is, anything is meaningless. Okay. Now, let us draw the free body, let us draw the bending moment diagram. The bending moment diagram become like this, very similar to the previous case, but the only difference here will be, now again you can check this equilibrium is satisfied, MBA plus MBC is equal to 0, MCB plus MCD is equal to 0. Okay. Now, the equilibrium, the bending moment diagram becomes, at this point it is, at B it is 40.625, and then at C it is 59 point something. So, these bending moment you get from this is the bending moment you get from the joint, and then corresponding bending moment from the external load. This is this. Okay. And then for so your bending moment between bending moment become this. Okay, this part is negative, this is negative, and this is positive. And similarly, bending moment for this is 40.625, this is 59.375. Okay, and again it is 40.625, and this value is 9.375, and this, and again here it is 59.375, and this value is MDC 40.625, this is 40.625, and finally this become this, and then your bending moment is this. your bending moment. Finally, bending moment become this. Okay, please. This is this. Please check these values. Once you have this. Okay. Now, next is what we do is we stop here. Now, let us just summarize what we have learned in this week. Okay, we discussed the overall concept of displacement method, and then that concept is translated. I mean, is written. There are three kinds of displacement method we'll discuss in this course. One we have discussed is slope deflection method. Now, another two methods, which is moment distribution method and then direct stiffness matrix, that we will discuss in the subsequent weeks. Okay. Now, please do some exercise. The concept, once you understand the concept, that is fine, that is absolute necessary. But just by understanding the concept is not enough. You need to apply that concept through. You need to, in order to appreciate that concept in a better way, in order to comprehend the concept in a better way, you need to really apply them to different problems and do some exercise. Some of the problems we have demonstrated here, but those problems are relatively simpler in terms of number of unknowns and in terms of loading conditions and the boundary conditions. But once the idea has been not to, as I said earlier, idea has not been to solve any particular structural analysis problem. The idea has been to demonstrate the concept through some problem, through some relatively easier problem. Okay. So, so next week what we do is next week see what is moment distribution methods. Okay. Then see you the next week. Thank you.